Okay, so this is the second half of our static equilibrium problem. Remember, the first half had us looking at what strength of rope are we going to need, what minimum tension or breaking strength do we need in that rope in case this system collapses and we have to replace that rope. And we found in our torque analysis, when we did that torque analysis, setting the pivot point at the location of the wall, that our torque analysis gave us a tension of 2262 newtons. So the second half of this question is really looking at what is the force being exerted by this pin. If we had to replace that pin, what force is being exerted by that pin on that beam that we have been analyzing? So we did an extended free body diagram to look at the torque analysis. And when we set our pivot point at the location of the wall, we got rid of those two forces because we didn't know how to analyze the torque of them because we don't have the force associated with them. Now, sometimes when we want to look at the force or a value on another element that's acting on an object, we might just select a different pivot point and redo the analysis. Unfortunately, that's not going to work in this case because I have two forces. Remember, the horizontal and the vertical force. So two unknowns that I would still end up with at the end of my analysis and only one equation. So we look for other strategies. Now, we know that this is in static equilibrium, so it's not rotating, and it's also not translating. And previously, we had up here that the sum of the forces equals 0. So let's do a force analysis on this situation. Again, we're going to not do the force tree. We've already talked about all the interactions. There were 5 forces that we dealt with the torque analysis. So those same 5 forces are going to show up on the free body diagram of the beam. And we're going to take them and sandwich them together. So there is our dot, our free body diagram. And if we look at the forces acting on that beam, what do we have? Well, we had that force of gravity of the beam. We had the force of the crate on that beam. We had the vertical force of the wall and the horizontal force on the wall of the wall. And then we had the tension. So go back in part A and you look at that extended free body diagram. If I were to take that and collapse it all down to its center of mass and look at the forces acting on it in a translational way as if it's moving about its center of mass, then these are the 5 forces that we've already been examining. And so just like with every force analysis we've done in the past, we're going to number these 5 forces. And typically, I'll use the same numbering system as I do with my extended free body diagram. But because I erased all of that and didn't make note of what those were, we're just going to renumber them in this manner. And we're going to separate them into their horizontal and vertical components. And then apply our relationship for the fact that we're in equilibrium. So force number 1 is the force of the crate. There is no horizontal component, and we know that crate is exerting a force equal to its mass of 1960. Force 2 is the force of gravity. Again, I went too fast. That direction is negative, so we always want to remember to put in that direction explicitly. Force number 2 is the force of gravity. That's given for us at 1200, and it also points in the downward direction. Force 3 is our wall in the horizontal direction, and it's pointing in a positive direction, and there's nothing vertical. Force number 4 is the vertical component. It's also in the positive direction and only acting in the vertical component. And then force number 5 is the horizontal component of our tension. So we know that this angle is 50 degrees. That's given in the problem. So our horizontal is adjacent to that 50 degrees, so it's the cosine, and it's pointing in the negative direction. Our vertical component of the tension is the tension times the sine of 50 degrees, and it's pointing in the positive direction. So because I'm using that internal angle, I'm making sure to explicitly look at those directions. Okay. Now we recognize that this is an equilibrium, so the sum of the forces horizontally are 0, and the sum of the forces vertically are equal to 0. So let's add these up. we have the force of our wall horizontally minus the tension times the cosine of 50. That's going to equal 0. So the force of our wall horizontally is equal to the tension times the cosine of 50. And I'm noticing I don't have my calculator in front of me. All right, so the force of the wall horizontal is equal to, and now just hold that thought while I grab my calculator. All right, this is called being prepared. Okay, so our tension we calculated at 2262 times the cosine of 50 degrees. It gives us a horizontal component of 1453.99. And I'll just keep some extra digits so our rounding isn't so horrible. All right, now the vertical component. Well, I add these up, minus 1960, minus 1200, plus the force of the wall vertical, plus the tension times the sine of 50. That's going to equal 0. And again, algebraically, I'm just going to solve for the force of the wall vertical. So I have 1960 plus 1200 minus the tension times the sine of 50. So my force of the wall vertically, 1960 plus 1200 minus 2262 times the sine of 50 is 1427.2. So here are the two components. I expected the horizontal to be positive. I expected the vertical to be positive, so that's a good thing. So how do I get the force of the wall? Well, this is that algebraic stuff again. So the vector algebra. So the force of the wall is going to be the square root of 1453.99 squared plus 1427.2 squared. So the magnitude then, so square that, plus 1453.99 squared, second square root, I get a magnitude of 2,037 newtons. And my angle is the inverse tangent of the y component, 1427.2, divided by the x component, 1453.99. And that gives me 1427.2 divided by 1453.99, 44.5 degrees. So that gives me the magnitude and direction that that force, that pin, is exerting on the beam. All right, so we've determined the tension using the concept of a net torque being 0. It's in rotational equilibrium. But we're also in static equilibrium. So we can examine the translational forces, set those equal to 0 since it is in equilibrium, not changing its motion, and use our knowledge and our abilities in force analysis to determine the force on the wall. Good job.